additive manufacturing has exploded into a multi-billion-dollar industry. Design files now travel across organizational boundaries, getting printed on remote or third-party machines. Even when those files are encrypted in transit and at rest, the physical printing process itself leaks information through unintended emanations. You don't need cyber access to steal intellectual property. You just need a microphone, an accelerometer, or a power meter. These are side-channel attacks. In 3D printing, researchers have demonstrated that acoustic noise, mechanical vibration, electromagnetic radiation, power draw, and even thermal emissions can be used to identify or reconstruct printed geometry. In response to this threat, Bambu Labs shipped active motor noise cancellation, or AMNC, across their A1 Mini and P1P printers. AMNC is a hardware-level countermeasure that uses adaptive current control to suppress motor resonance frequencies. It's the first commercially deployed defense specifically targeting acoustic leakage in consumer FDM printers. But by design, it only addresses airborne sound. It leaves structural vibration, power, and electromagnetic emanation completely untouched. So the critical question is, does AMNC actually neutralize the acoustic channel? And more importantly, what does it leave exposed? To answer this, we're looking at the first empirical evaluation of a deployed hardware countermeasure on a public dataset. The dataset contains synchronized iPhone audio and triaxial accelerometer recordings from both a Core XY P1P and a Bedslinger A1 Mini. We're working with 12 distinct object classes, 6 paired recordings per object per printer, giving us 144 synchronized audio vibration pairs. Recording durations range from under 2 minutes to nearly 3 hours, reflecting vastly different toolpath lengths and movement profiles. The threat model here is a passive, physically proximate adversary. They don't hack the printer. They just sit nearby with a microphone and an accelerometer. Their goal is closed-set classification, identifying which known design is currently on the build plate. A labeled corpus from prior print runs enables supervised learning. The cross-printer experiments test whether that calibration transfers across different machine architectures. For feature extraction, we process the audio at 16 kHz, extracting 32-dimensional vectors including 13 MFCCs, spectral centroid, bandwidth, roll-off, and zero crossing rate. We also simulate an AMNC notch filter bank across multiple quality factors to model additional acoustic suppression. For vibration, we start with summary statistics per axis: mean, standard deviation, RMS, peak-to-peak amplitude, and dominant FFT frequency. That's a 15-dimensional vector per recording. For temporal analysis, we divide each recording into 120 ordered segments, computing per axis RMS, standard deviation, peak-to-peak, and dominant frequency per segment. That gives us a 120-by-12 sequence, z-scored per recording to isolate temporal shape from absolute amplitude. Classification is handled by a random forest with 200 trees, standardized features, and grouped 5-fold cross-validation. We also test gradient boosting, SVMs with an RBF kernel and k-nearest neighbors. The temporal attack uses a dilated one-dimensional convolutional neural network over the full sequence, averaged over 3 random seeds. Every result is validated with Wilson confidence intervals, a 200-sample label permutation null hypothesis test, and an order shuffling control to verify sequential dependency. Let's start with the acoustic channel under active AMNC. The results are definitive. Classification accuracy sits at 12.5%, with a 95% confidence interval that fully encompasses the 8.33% random baseline. Even when we layer a simulated notch filter on top of the hardware countermeasure, accuracy stays at chance. Across all tested quality factors, the acoustic channel is statistically indistinguishable from random guessing. AMNC does exactly what it was engineered to do. It neutralizes the airborne acoustic side channel. But structural vibration tells a different story. The vibration channel leaks a real, measurable signal. With summary statistics alone, we achieve 31.25% pooled accuracy. That jumps to 36% on the A1 Mini and 47% on the P1P when evaluated within printer. A label permutation test confirms this isn't noise. The p-value is 0.005. But is it geometry or just duration? A feature ablation isolates the signal. Amplitude and offset features reproduce nearly all the accuracy at 29%, while frequency-only waveform features drop to chance at 6%. Stable metrics like standard deviation and RMS retain 27%, ruling out a pure recording length artifact. The summary leak is coarse, amplitude-driven magnitude, not waveform shape. Here, where the attack becomes significantly more dangerous. When we feed the full ordered sequence of 120 times segments into a dilated 1D CNN, accuracy jumps to 60.65%. That's roughly 7 times the chance baseline. Crucially, when we shuffle the temporal order of those segments, accuracy collapses to 32.64%. The 28-point gap is far larger than seed variance. This proves that a substantial component of the vibration leak is genuinely sequential. The macroevolution of the print trajectory carries geometry-correlated temporal structure that static summary statistics miss. However, this signal is highly device-specific. When we train a classifier on the P1P and test it on the A1 Mini, accuracy plummets to between 11 and 12.5%, right back at chance. The Core XY gantry and the bed slinger design produce fundamentally different vibration transfer functions. An attacker can't just deploy a universal model. They need per-device calibration, which raises the cost and complexity of a real-world attack. So what does this mean for security? First, AMNC must be understood strictly as an acoustic-only control. It solves the microphone problem, but it leaves structural vibration completely exposed. A defender who assumes AMNC covers all physical leakage is operating with a false sense of security. Mitigating vibration requires dedicated countermeasures, chassis-level damping, anti-vibration mounts, or randomized stepper acceleration profiles that deliberately decouple motion from toolpath geometry. Each of these trades off against print quality, speed, or hardware cost, so deployment requires a concrete security versus performance budget. Second, the device specificity we observed is actually a defensive asset. A heterogeneous fleet of printers with different mechanical architectures forces an attacker to calibrate models per device. That's a natural, low-cost layer of protection that a homogeneous fleet simply doesn't have. Third, and this is critical, the threat demonstrated here is closed-set identification, not geometric reconstruction. We're confirming which known design is on the bed, not recovering arbitrary unknown geometry. That's still a meaningful risk for espionage or supply chain monitoring, but it's bounded. The temporal result, however, shows that geometry-correlated information survives into the vibration channel. Identification is the floor, not the ceiling. Full reconstruction-grade attacks would require tapping into the magnetic or power channels, which AMNC also leaves untouched. This study has limitations. We're working with 2 printers from a single manufacturer, 144 recordings, and 12 classes. The temporal model's capacity is bounded by this scale, though we've mitigated overfitting through grouped cross-validation, permutation testing, and multi-seed averaging. The task is strictly identification, not reconstruction. And AMNC runs continuously during collection, so we're measuring its effect in situ rather than through a controlled on-off causal study. Future work naturally follows these findings. Scaling the dataset across multiple manufacturers, printer architectures, and non-FDM processes like SLA or SLS is essential for external validity. Moving from classification to sequence-to-sequence regression against ground truth toolpaths or G-code is the proper test for reconstruction capability. Jointly collecting power and magnetic channels will likely be the route to full geometric recovery. Stronger temporal architectures, like attention mechanisms or reservoir computing, could push past the convolutional baseline. And finally, vibration-specific defenses need to be deployed and measured against concrete trade-offs in print quality and throughput. To wrap this up, AMNC is a successful targeted defense. It effectively kills the acoustic side channel. But cyber-physical security isn't about plugging one hole. It's about understanding the full emanation landscape. Vibration remains a partial, geometry-correlated leak, driven by amplitude statistics and sequential motion patterns. It's device-specific, bounded in this dataset, and insufficient for full reconstruction on its own. But it proves that hardware countermeasures must be evaluated holistically. Securing additive manufacturing against IP theft requires multi-channel awareness, not just acoustic masking. All code and the dataset are publicly released to support further research. The conversation around physical layer security in manufacturing is just getting started.